Hey guys, this is the Academic Chemistry, Chapter 8, Section 3, Bonding Theories. So today we're going to talk about VSEPR theory, which is a fun sounding word if you want to go ahead and try and pronounce it. But let's get into what it actually means. And then eventually we're going to come back to this picture and you'll hopefully laugh. All right, so what is VSEPR theory? So molecular shapes is the whole name of this chapter or this section. And basically you're going to predict the shape of a molecule using valence shell electron pair repulsion theory. Woo! Lots of words, but I promise it's really not that hard. So basically, what the VSEPR model tells us is that there's interactions happening around a central atom. So, and there are lone pairs or there are atoms surrounding it. And you kind of have to think about what each one would do to other things. So for example, in this, we've got boron as our central atom, and over here as well, we have boron as our central atom. So you can see that these have different shapes to it, and that's just predicted using the VSEPR theory. Like, where are those other atoms in relationship? So you have to remember that electrons are all negatively charged. So electrons in bonds and electrons in lone pairs all repel each other. Remember, opposites attract, but like charges, so negative charge to negative charge, those are going to repel and they want to be as far apart as possible. Let's go through some examples. If you have Cl2 or anything that just has two atoms in it, the maximum bond angle has to always be 180 degrees because you can't have any other angle when you have just two things next to each other. If you have two things next to each other, it's always going to be a 180-degree difference between the two. So in carbon dioxide, though, you have three atoms. So what is that going to look like? Well, the furthest we can put them away from each other is still 180 degrees. So that's what this looks like. In BH3, boron trihydride, the maximum angle between the boron hydrogen bonds are, well, if we draw the Lewis structure, it looks like this. And that evenly spaces out to be 120 degrees between all of them. So 120, 120, 120, that's 360. That's our whole circle. But things get a little weird from there. So if you have methane, CH4, you would expect it to look like this. However, methane or fart gas, CH4, it's not actually a square like you see here. So the Lewis structure, you have to remember, is the two-dimensional representation, as in left and right, up and down only. Those are your two dimensions. But in real life, molecules are three dimensions, which means they are left and right, up and down, but also front and back. They have that extra dimension to them of depth. So CH4 forms a three-dimensional shape called a tetrahedron. Whew, that one always gets me. And we actually did this in your lab. When you dipped that pyramid into the soapy water, you could see that the angles, where the soap connected, that actually made the structure of methane. So it looks like this. Instead of being just up, down, right, left, some of them come in and out of the plane. So if you see this dashed line here, that dashed line means it's actually behind what you're looking at. So it goes that way, behind your screen. And see this solid, thicker line? That's going towards you. So one of my chem teachers described it as the dotted line looks like footprints of someone running away from you, right? So this hydrogen is actually behind your computer screen. And then the thick line looks like a knife coming at you. So that's coming out towards you. Not in a scary way, but yes. And then these two are within the plane of your computer screen right here. And that gets them even further apart than this 90 degrees. It actually gets them 109.5 degrees apart from one another. So they are nice and evenly spaced out. So the electrons in their bonds are happy. They have as much space as possible. How about PCl3, phosphorus trichloride? Phosphorus trichloride, on the phosphorus, the central atom, there's an extra lone pair of electrons. So, ta-da! Now that lone pair is going to actually take up all of this space. and that space is a purely negative region. If you remember, these bonds here are all attached to atoms that do have a nucleus in them, which means they have some positive charges somewhere in them. But this lone pair is just straight up negativeness. So because it's straight up negativeness, it's going to actually push everything else away. So it kind of does that with the molecule. So it has four regions of electrons around it, like methane had. See, it has a region here, and then each bond represents a region. But because it has a lone pair, that lone pair pushes everything, all the other bonds further away. The lone pair has a stronger repulsion than any bond does. So it actually reduces the angle, your bonding angles, to 107 degrees. So lone pairs have denser concentrations of negative charges than just the electrons in a bond. Because it has such a strong electron concentration where that lone pair is, it pushes the other electron regions, which are the bonds, closer together. So this is going to be kind of the modified Lewis structure. And then we can draw this. This pink and white would be called the ball and stick model. So that's saying like a ball represents where the atom is, the sticks are the bonds, and you can kind of see it a little more geospatially than you would in a regular Lewis structure. All right, so here is the bread and butter of your VSEPR theory. Ta-da! Okay, you're probably wondering how to read this. I got you. Up and down is going to tell you the number of electron regions around the central atom. What I mean by that is a lone pair is a region or a bond is a region. Single bond, double bond, triple bond, doesn't matter. That's one region, one area where bonding happens, or a lone pair. So when you do this, when you want to figure out what the shape is going to be, the first thing you're going to do is look around the central atom and see how many regions of electron densities there are. And then left and right, this is the number of lone pairs around a central atom, because you know that the lone pairs push the other atoms closer together, so you have to take that into consideration. So previously we went through this and said this had 180 degrees. Now out of this, carbon is your central atom, okay? If you look around carbon, there is 1, 2 areas of electron density. So the only option is for a linear VSEPR theory molecular geometry. So carbon dioxide is a linear molecule. All the molecules line up in a straight line. And this is what it looks like if you were to draw the ball and stick model. All right, how about boron trihydride? So we've already talked about this. We know it's 120 degrees because that's the max distance. But the other way we could think about it is look at the central atom, boron. There is 1, 2, 3 areas of electron density. So we have 2 options for 3 areas of electron density. So you have to ask, does it have 0 lone pairs or 1 lone pair? So look at boron. There's no lone pairs, which means it's trigonal planar. And here is the ball and stick model of that. All right, methane. If you look around carbon, that central atom, you've got 1, 2, 3, 4 areas of electron density. We have 3 options. So look at carbon. Do you see any lone pairs? I don't see any. So 0 lone pairs, it has to be tetrahedral. And again, here is that ball and stick model if you're asked to draw something like that. Phosphorus trichloride that we talked about earlier. If you look around, you have 1, 2, 3, and then you have a 4th region of electron density. So always between 2 atoms is a region of electron density from a bond, and a lone pair makes a bond or makes an electron density area. So again, 1, 2, 3, 4. So this is the same geometric family that methane was in, but because it has that lone pair, 1 lone pair on phosphorus, it's actually going to be the trigonal pyramid shape. And the ball and stick model looks like this. So everything's pushed down a little bit further. All right, so I want you to try this for yourself. If you have chlorine trifluoride, what shape do you think it would make? Freeze a computer, draw out the Lewis structure, go through the steps, and see if you get my answer. All right, so Hopefully you got that it was T-shaped. And if you didn't, you need to figure out why you didn't get that before you move on. So now that you've learned about VSEPR theory and how these molecules are spatially arranged, do you see the pun? Caution, wet floor. Okay, so hopefully you can figure out what molecule that is and what VSEPR shape it would make. Good luck with VSEPR theory, and make sure you talk to me if you have any questions. Otherwise, I'll see you in the next set of notes.